So before we move to this second, it just occurred to me that there was one question, that was raised last week. And I haven't seen any other questions. In fact, I was a little disappointed. I hope you guys put some more questions this week, and we can discuss them in the class. We will make time for that questions. So it's actually very valuable to ask questions and see what we can find. So the question was the degeneracy of the electronic states for writing the electronic partition function is given by 2j plus 1 or something like that. In the notes I gave you, it should be 2s plus 1, but it doesn't matter anyway. So why is that, and so on. So this is a very good question, and to synchronize this with the quantum mechanical descriptions that we talk about in my other course, the degeneracy is given by 2s plus 1. S is the total spin quantum number of the system, of the molecule. So most molecules have paired electrons. All electrons are paired up in most molecules. So each electron has so plus half or minus half spin, and if you add them all up, you get the total spin quantum number. And so plus half minus half, plus half minus half. If you have even number of electrons, means all electrons are paired out, the total spin quantum number is 0. So the degeneracy 2s plus 1, 2s is 2 times 0, plus 1 is 1. So you got degeneracy 1 for most molecules for the electronic state. And this is what happens. And there are some exceptions. For example, oxygen molecule has two electrons that are not paired. And so in that case, the total spin quantum number is, plus half and plus half, or minus half and minus half, we can take that way. And so there are three different possibilities you can get. And then the corresponding states, the three different states will come out, because S is plus 1, plus half is 1. And so the total spin quantum number is plus 1. So 2s plus 1 is 3. And so you should get 3 states that are degenerate. And so the 2s plus 1 equals to 3. So we call this as the triplet state. And so the triplet state has 3 individual states that are equivalent in energy. And in one state, both electrons are up spins. In other state, both electrons are down spin. In the third state, one electron is up and the other electron is down, but they are in different orbitals. And so they're not in the same. So that is called the T0 state. So T plus 1 state and T minus 1 state, T0 state. And so there is all 3 states are identical in energy until you apply a magnetic field. Then they start to split up, and you see the transitions between the states and so on. So the oxygen molecule, you have 2 electrons, parallel spins, so plus half and plus half. So the total spin quantum number is 1. Therefore, 2s plus 1 is equal to 3, the degeneracy of the electronic state. And so you need these degeneracies to write the partition functions, right? So that's the electronic degeneracy. So this was the question, how to do this and why it is this way. So that's the explanation for that. Okay, so I'm glad I remembered that. Yeah, so Joe, go ahead.
Yeah, so I guess when I think of degeneracy, I think of something that's the state that has multiple possible states that it can be in, and they have the exact same energy. Yep. But if we're talking about like the quantum number J, for instance, that would be like the rotation of the molecule. So if we're talking about the electronic portion of the partition function.
The confusion. I think that was some silly mistake. It should not be J, it should be S, the spin quantum number, not the rotational quantum number.
Right. I guess like for any kind of angular momenta, though, wouldn't that necessarily break the degeneracy?
Absolutely. Okay. Absolutely. That's exactly what you're talking about, right? So in a molecule, when you have all these electrons filled in and everything, the degeneracy of the electronic state, right? This is the electronic state. purely. And we're not talking about the rotational or vibrational or other things, because those are different. They have different degeneracies. So the electronic state degeneracy is mainly due to the spin quantum number of the electrons that we have in our system and how they couple and what is the angular momentum of those electrons. And we don't consider nuclei in that state. We only consider the electrons and their angular momenta. So you calculate total angular momentum, spin angular momentum, and then look at how many states are possible within that. And so that's how you calculate 2s plus 1.
Yeah, I guess the hang up I guess I was having is that, like, how far do we go that we actually consider a state degenerate, if that makes sense? Like, so if we have an electronic state, there's multiple different rotational states, but the reaction of the rotation of the molecule with that electronic state breaks that degeneracy.
Yeah.
But then within each rotational state, the reaction with, like, for example, a nuclear spin or something breaks that degeneracy, and so on and so forth. But
so all different energy states, for example, rotational, vibrational, translational, they all have their own degeneracies. And so when we are writing the partition function for the electronic state, though, what we're doing is we're considering just the electronic state and its partition, how the energy is partitioned within that state. And so it is essentially insulated from all the others. So in other words, energy, it doesn't flow back and forth, or if one state doesn't affect the other state. That's the assumption made in there. It refers back to the von Oppenheimer approximation there. And so we assume that these systems are independent of each other. So in other words, if I populate a translational state, it's not going to leak into the electronic state. That's the assumption made. And so the degeneracies of other states don't affect the degeneracy of the electronic state. And so,
whenever
you're,
so whenever you ask about, like, degeneracy of electronic state, we're kind of ignoring rotation or other
unless you say it is coupled system.
Okay.
Yeah, unless you say it's a coupled system, then you have to worry about all those things. And so, so that's why we write the partition function each energy state separately. We are assuming they're not connected. Otherwise, it gets very complicated. So that's the simplest solution to the problem. To assume that they're not connected. Yeah. So the rotation of the wheel is not related to the rotational motion of the car, but of course the rotation of the wheel is related to the motion of the car. So if you want to separate the two systems, you have to assume they're independent, then do the analysis, and you can come back and say coupling factor. You can attach that as a correction later on. So there will be an undoubtedly crossover from the electronic to the rotation, vibration, other things. And but that effect is much less compared to the pure states in determining the outcomes you're looking for. So we are assuming for the moment they're independent of each other. So that's the deal with that. And so now let's see what is the mechanism, how we go about doing it, or figuring out what the mechanism is. And this is a big deal in organic chemistry. They do lots and lots of experiments for years and years, and in the end, they may not even know what the mechanism is, right? And from physical chemistry point of view, we can do calculations, dynamics, and then from that, we can figure out the lowest energy path connecting the reactants with the products. Again, as I said before, one-dimensional surface, we can write that one-dimensional surface, and that describes the detailed path. And so that's the mechanism of a chemical reaction. So we'll define what the mechanism is and molecularity is, elementary step. Then look at Lindeman's mechanism as an example. And again, this is so fundamental, it permeates through chemistry, biology, physics, everywhere. And almost every model is derived from it one way or the other. And even when it is not acknowledged that way, you can see that passing through. Mechanism of reaction is elucidation of detailed individual steps that can be established for the overall transformation. So individual steps, meaning that A goes to B, B goes to C, and then C goes to D, and the D is the product, A is your starting material. So what are these things in between? That's the question we are asking. Elementary reaction is the one that has only one step by definition. There's no other step in between. So you may have 5 elementary steps connecting the reactant to the product. That's fine. But each step is an individual step, and you cannot break it down any further to another elementary process. So that's one unit, for example, like that. So HO2 goes to H plus O2. So that's the decomposition of HO2. It's an unstable radical, and the hydrogen-oxygen bond is breaking, giving rise to O2 molecule and the hydrogen atom. So that's a one-step process, and so that's the elementary reaction. And then you have the rate of that elementary process. You can write very easily because that's a reaction, chemical reaction. D is I over V by dt. So that's the rate of change in the progress per unit volume is minus K times concentration of HO2, right? Concentration of HO2 raised to the power 1. And because that's an elementary step. So the order of the reaction here is 1 for that with respect to that reactant. For that particular step, you can write the order. And so first order unimolecular process. Unimolecular because there's only one molecule is involved on the reactant side. And H2 plus I2 goes to 2HI. So this is now 2 molecules reacting. And in one step goes first to the HI. This is known, well understood, and established that this works this way. There are no intermediate steps in between. And so there's one elementary step, and this is an exception. Most reactions don't go this way. So elementary bimolecular reaction. Bimolecular because you have 2 molecules reacting to give rise to the product. Here you have only 1 molecule reacting to give rise to the products. And so that's the or radical. So that's how it is. So in case of this, H2 plus I2 is extensively studied. I don't know how many thousands and thousands of papers have been written on this fundamental reaction, because there's so much to learn about this reaction. So schematically, what we know so far is that H2 plus I2 then goes into an activated complex of a distorted rectangle, for example. Then I bond is half broken, IH bond is half formed, and HH bond is half broken, and HI bond is half formed. And so some bonds are being formed and some bonds are being overstretched and being broken. So this is the structure of the activated complex. It's not the transition state. And this is the activated complex. And so then it can decide to go back. And so that you can do that by breaking the HI bond, partially formed bond here, and HI partially bond here. Those two can be broken simultaneously. Then you get back H2 plus I2. On the other hand, if you break horizontally the HH bond, II bond, then you form the HI bond fully and HI bond fully, you get HI and HI. So either the system, this activated complex can go forward this way or back to the starting material. And so this is now very well understood. And so in fact, we take something like that in the 7th module, and then calculate the partition functions for this structure: translational, rotational, vibrational, and electronic. And we assume that they're not couples, and so we can use the methodology we applied. And then from that, we calculate the rate constant, and then check whether our rate constant has really any reality to it by checking the experimental value. And then the experiment says, yeah, you're right. What you calculate is correct. That's the triumph of physical chemistry. And at least for very, very simple systems, we can calculate the rate constants pretty well within 10 to 20% error, which is kind of experimental error anyway to begin with in many cases. So all these things we are discussing about and talking about work fairly well. And not when you talk about exactly 3rd decimal or 4th decimal, yeah, that's a different story, but it gives you order of magnitude correct answers. Even the basic model without any corrections applied. So the order of an elementary step is given by the, whatever you write, 2 of A goes to product, and then C squared, concentration squared, because 2 of A going to product. So if it's elementary step, then rate is given this way. Rate is equal to the rate constant of that step multiplied by concentration of A squared. So if once you have written a mechanism by writing these individual steps, And sometimes you don't know what they are, right? So you just write all possible ways you can write a mechanism, all possible steps, single steps, and then you can rule out some and confirm the others by your calculation, see if the calculation works out with the experiment or not. But the point is that if anytime you write an elementary step, you know the order and you know the rate, and you associate a constant, rate constant with that. So that's the key concept in mechanism. A plus B goes to products, then rate equals to, it's a second order reaction. We said that already. It's a bimolecular and second order. So here the molecularity and order agree because it's an elementary step. Only in the elementary steps this agreement is followed. And so the rate is then K and Ca multiplied by Cb, concentration A versus concentration B, multiplied together, raised to the power 1 each, right? A plus B plus that. And so A plus B plus C, that is an elementary step. Then the rate is simply equal to rate constant multiplied by concentration A, concentration B, concentration C. And so we can write the rates for each of the individual steps right away. As soon as you've written the mechanism this way, you can write the rates for each of these steps individually, right? And then you can calculate the overall rate, and based on how the reaction is proceeding, and we'll see the example of that. So let's say unimolecular decomposition. This is the Lindemann mechanism, very famous, and put forth and explain lots and lots of experimental data very, very well. And as I said before, this is a very kind of a broadly applied mechanism in chemistry. And so the A goes to products. You ask what is the rate determining step, and how does the rate constant change as you change the concentration of A, B, C, whatever involved in it. So here, unimolecular decomposition, that is the basic simple model, means that you have certain A and that goes to product, and that's it. There's nothing else, no B, anything else happening. So how does this work? And we already said that even if it is a unimolecular decomposition reaction or isomerization reaction, it goes to products. We invoked the activation energy concept requires that A reacts with A or collides with A, not necessarily react, make A star. It's a much higher on energy in A star compared to A. So in other words, if you're walking by the Broadway in Manhattan, New York City, and then a mugger comes by and mugs your money, and so now the mugger has the money and you are lost. And so, so that's basically an encounter there on the Broadway, and one of the two ended up with the cash between the two, and so that's the person richer and that person poor. So now this rich person can now undergo a chemical reaction because now it has enough cash to buy the product. So let's say K1 is the rate constant for that, and then that is to produce A star from A. And then A star can react with another A, and this A can rob that. And so both become now poor, and they evenly divided up the cash, and one doesn't have more excess energy anymore to undergo the chemistry. And so this is internal deactivation happening. So, this what we have done is a forward step and a reverse step. Even though it's a forward arrow, A plus A is here and there. And so A star plus A is in the forward here, A star plus A is in the reactance side here. And so this is your equilibrium already put in together. So that's a K minus one, simply because the products becoming reactants, and so products become reactants, so the reverse of that, so K minus one. This doesn't mean the K1 and K minus one are somehow related. No, they're not related. They were just symbolizing them in a way we can recognize what they are. So they may be equal, may not be equal, may not have any relationship whatsoever, but the ratio of those two is the equilibrium constant. So that we understand. So A star goes to products. So nevertheless, where A star is produced, in the end, A star goes to products. That's our key model for the activation energy. And so that A star goes to products is the K2. And so now A star is being constantly produced, and some of that goes to products, some of it goes back to A. That's the key mechanism. So three-step mechanism. And so we ask, what is the rate determining step, and how you get the rate constant out of this, and How is it related to the measured value in the lab and all those questions, legitimate questions? And so the rate of production product is equal to the rate of consumption of a dCA by dt, right, is equal to minus K2 times S star, concentration of S star. Because in the end, K2 is the one that is making a product. K1 and K minus were not making products directly. So by definition, dCA by dt, the rate at which A is producing the product, is equal to this rate constant K2 multiplied concentration of A star, but with a negative sign, of course, because the decrease in the concentration of A with respect to time. So steady state approximation is used here to solve for concentration of A star, because concentration of A star, we don't know what it is. We have to express that in terms of A, okay? Because we know the concentration of A, not the A star. And so we need to rewrite this in terms of concentration of A, and that is done using steady state approximation. Now, this approximation is very popular and famous and useful, and of course, it's still an approximation. It can break down if certain conditions are not met. So what we're saying is A star does not accumulate. If A star accumulates to any significant extent, then the approximation fails. And so question is, what is significant or what is insignificant, right? So this is a constant debate. At what stage we call this is significant and so on and so forth. But what it means is it doesn't accumulate. It goes up and then constant will bleed out. And so its concentration doesn't increase. It goes to some value and then stays. It doesn't go any higher with time. It stays the same. So that is valid. So and it's not a stable product. So those are the two things that you think about when you say steady state approximation. Rate of formation of A star, rate of consumption of A star. I'm running out of time here. So constant A star, the time is 0. Therefore, K1 C squared A equal to 0 as well. And therefore, excuse me, the rate of formation of A star is given by the rate of production, which is involving the first step, C squared A, and then the rate of consumption, this one and this one. So that is the second step, that's the third step. Then you can solve for it. Concentration of A star is given by this ratio. So we can now plug that into that. And then the next slide here, you see plug that into that. And then you get dCA by dt equals to K1, K2, C squared A, K minus 1, CA plus K2 with a negative sign. This is just algebra moving back and forth. And it shouldn't confuse us too much. Just too many symbols, so it could be confusing. But anyways, so that's your, if dCA by dt, if K minus 1 CA, right? So K minus 1 CA here in the denominator is very, very small. You can ignore it. Okay, it's 0. And then that K to K cancels away for minus K1 C squared A. That's limiting case. It's a second order reaction. It depends on the square of the concentration of it. If, on the other hand, K minus 1 CA is very, very large compared to K2, the K2 can be put as 0 here, and then K1 by K minus 1, and CA and 1 CA cancel away. And so they have K1, K minus 1, K2 times CA in the first order reaction. So depending on the values of these K minus 1 and CA, we can switch it from first order to second order. So this is a very interesting way you can manipulate how you want to run this reaction. So in summary, we looked at a simple bimolecular looking Lindemann mechanism. It's a unimolecular decomposition reaction, but it involves collision between two molecules to give rise to the product. And so we made a composite rate expression, and this is valid for a whole bunch of different things. So we really ran out of time here. But I suggest, look through these assignments, please upload them and make some questions or whatever you have in mind so that we can pick them up in the next class, in next week. So the exam will be up at 9 o'clock on Thursday morning. And so familiarize yourselves with the lockdown browser, get ready, download the equation sheet, please print it out so you have it handy. So we'll stop sharing here and we'll stop recording.